Howdy folks, Mr. Reed here, and welcome to One More Question. So for today, what we're going to take a look at is stretching, horizontal, vertical, and specifically we're going to go graph to graph. So I'm going to have a picture of a graph that's going to pop up, and we're going to see a second graph that's also overlaid on the same axes. We're going to come up with an algebraic equation which allows us to relate the second graph to the first one. What we're going to do is we're going to write a g of x that's appropriate given the transformation that happens from f to g. All right, so if that's what you're looking for, let's get to it. So as you can see, the graphs are up beside me, and what we'd like to do is algebraically write an equation that would be of this form right here. So it's going to be g of x is equal to a onto f of bx. Now, we don't actually know whether a or b or both will be required for this particular type of question before we take a look. Since I'm doing this at a mild level first, I'm going to actually only do one at a time. So it's going to be either A or B, but we still have to decide which one of those two is actually happening in our example. So I'm going to take a look at the graphs first and notice that f of x and g of x have the same general shape to them, except for g of x looks like it's been squished. So it's been brought in this way. Now, as soon as I've kind of done that with my hands, that should be a big sign as to which sort of stretch is going on. So things that are this way, side to side, in or out from the y-axis, those are horizontal. So along our horizontal axis is the direction of the stretch or compression, if you want to call it that. And in this case, we're getting smaller as well as going along that horizontal axis. So since it's a horizontal axis type of thing, that means we are going to have a B, yes, and a no for the A. What that actually means is that the A value is 1, but a coefficient of 1 is the same thing as not writing it in. So that's what I'm going to do. I'm just going to not bother writing it in. All right, so now we have to decide, we have to find some appropriate point that will allow us to determine what the stretch actually is. Now, because of the type of transformation that we're doing, we're not going to find that it's going to stretch a different amount at different locations. That would be very difficult to deal with and hard to write down algebraically like we're doing right now. So this is just a single stretch factor for the whole entire function. And so I'm going to take a bad point first. There's actually only one bad point, and that would be this one right here. The one that's located at the origin. And what I mean by a bad point is, we'll notice that it actually doesn't move. It's what we call an invariant point. So under this particular transformation, it doesn't move at all. And the reason why it doesn't move is because it's right on the y-axis to begin with. So it's 0 distance away from the y-axis. So when we compress or stretch it away from the y-axis, there's no multiplying factor that can take 0 and make it turn into something else. So in this case, no matter what our b value is, it's going to end up right there anyway. So we can't get any clues as to what the b value is from that point. But that's okay. We have 3 other points, all of which would tell us what we need to know. So I'm going to take this time the point that is way out here. So that is at x is equal to 4 on the original function f of x. Now, if I look at the two graphs, I can pretty much tell that this over here was kind of the short arm of f, and this is the short arm of g. And so those two parts are associated with each other, which I'm pretty sure means that this point right here is the one that is paired up with the one I circled on f of x earlier. So what I'm going to do is say, oh, well, this one was out at x was equal to 4 units, and this one's out at x is equal to 2 units instead. So this is due to a stretch factor. I can tell that because of the squish that's gone on here. So this would be a stretch factor that takes 4s and turns them into 2s by multiplying. So what number do I multiply 4 by in order to get a 2? Well, if I took 4 times something, I'm going to put a question mark. That's kind of awkward, but I do that sometimes. 4 times something is going to be equal to 2. Well, if I divide both sides by 4, that means that the question mark, the thing that we're looking for, is going to be 2 divided by 4, which is the same thing as saying 1/2. So that stretch factor is 1/2. Now, I could have done that with a different point. For instance, if I took this point right here, that's at 3, it goes down to 1.5. that is still a stretch factor of a half. So 3 times a half gives us 3 halves, or 1.5. If I took the 1 over here, -2, and I multiplied that by a half, that would give me -1. That's good, because that's where that point is on the g of x function that's associated with it. And of course, 0 times a half just gives you 0 again, so nothing really interesting about that, but it lines up anyway. So this is the tricky part because it's horizontal. The vertical is really straightforward. The horizontal, we have to really commit to memory that the stretch factor is not the same thing as the b value. The stretch factor and the b value are related by a reciprocal. So we have 1/2 as the stretch factor. That means it's 1/2. So 2/1 is the reciprocal, and that's going to be the b value. So when I write my final answer here, g of x is equal to, no a value, f on 2, and we said that it was going to be 1/2, reciprocal of that is 2/1. The simpler way of writing 2 divided by 1 is just 2, and so we would have here g of x is equal to f onto 2x, and so that is our transformation that's going on here. It's a horizontal stretch, and the b value is a 2, which means that the stretch factor is a 1/2. So this second graph that's made off of a transformation of the original f of x piecewise function can be described as f onto 2x. All right, so that's graph 1. Let's do graph 2. That graph 2 that we have over there right now is the same original f of x function, but it's been stretched differently. And again, we can see that this one's gotten taller top to bottom. So that means that there's been a vertical stretch going on here instead. I'm going to rewrite, just for the sake of having it there, g of x is equal to a onto f of bx. You'll notice that I still haven't brought in the h and k if you followed along with some of the translation stuff I had done before. Those are going to get all mixed together soon, but we're isolating them first just to make sure we're okay and clear on this stuff. So a onto f, and then in brackets, bx. So in this particular case, we have vertical stretching going on, but apparently no horizontal stretching. And I can tell that because the original function goes from -2 to 4, and the new function goes from -2 to 4 as well. So it's the same horizontal distance, I guess you could say, from one side to the other. All right, so vertically, that's not true though. I actually have, and we can do it this way instead. So this is 2 units tall. And now I have something that is, instead of being 2 units tall, is 6 units tall. So I could take one individual point and look at the stretch value, or I could look at the size of the function and figure out my stretch from that instead. So if it used to be 2 units tall and it's now 6 units tall, that is a multiplying factor of 3. So we would get here an a value of 3 is going to do that. And we said the b value would not be needed. Same thing as saying is a b value of 1, not a b value of 0. If it was a 0, that would make the argument 0 every time. And that would be basically just smush it so that it was always the same point, which we don't want to deal with. That's not a really interesting case. So for us, g of x is equal to, and the nice thing about a vertical stretch is that the stretch factor is the exact same thing as the coefficient or the parameter value. So a actually is the stretch factor, so we just place the 3 in there, and then because the b value is 1, we're just going to write f of x. So it's g of x in this case, as the transformed function, is it just equal to 3 times the original function f of x. And if we wanted to do that with a point instead, just make sure you're understanding which points are going to be helpful to choose and which ones are not. In this case, both this point and that one lie along the axis. Multiplying them by 3 is not going to stretch them vertically at all. They're going to stay at a value of 0. So we either have to pick this point over here, which is at -2, or this point over here, which is at 4. So if we pick the 4 one, it used to be at -1, and then it goes to -3. So the question is, how do you go from a -1 to a -3 by multiplying? You multiply by 3. Double check the other point. So -2 is what it used to be for a y value. If we multiply that by 3, we have -6. That's exactly where that is right there. It's so coordinated. So we would have a -6 as the y value there. All right, folks. So those are a couple of short-ish examples, simple examples of stretches. So we did only horizontal stretch first and only a vertical stretch next. If you want to see how this looks when we have a couple stretches together and maybe involving some reflections, then you can take a look at the same topic but at a medium level that I'm about to record right after this. So thanks for hanging out. If you found it helpful, like, subscribe, and take care, folks.